Close your eyes for just 1 second. Blink. In that fleeting moment, light could have raced around our entire planet 7.5 times. 7.5 times. That's the sheer mind-bending speed of light. Now imagine that incredible speed multiplied not by seconds or minutes, but by an entire relentless year. The distance it covers. A staggering, almost incomprehensible journey we call a light year. It's a term tossed around constantly in science fiction and astronomy, a seemingly simple phrase. But what if I told you that truly grasping its meaning doesn't just change your perspective on space? It fundamentally alters how you see yourself, your life, and your unique place in the grand tapestry of the universe. It's not just a number, it's a cosmic truth, a barrier, and a revelation all at once. Tonight, we're not just defining a light year, we're taking a journey to the very edge of human comprehension. And by the end, you'll understand exactly why astronomers rely on this measurement, and why nothing else quite captures the immensity of existence. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now let's dive in. We live in a world of familiar distances. You know how far it is to the grocery store, to work, to the next city. These are distances you can relate to because you've experienced them. A kilometre. That's about a 10 to 12 minute walk at a normal pace. 5 kilometres, you can picture the drive, a few traffic lights, some familiar landmarks. 200 kilometres, that's a couple of hours on the road, maybe a pit stop, some snacks. These measurements are perfectly calibrated for our human scale, fitting neatly into our daily lives and experiences. We evolved to understand distances we could walk in a day, distances we could see crucial for survival and navigation, but these comfortable measures begin to buckle under the weight of true immensity. The distance from New York to Los Angeles is roughly 4,500 kilometres, about a 5-hour flight. People traverse it constantly, witnessing landscapes morph from bustling East Coast cities to the vast Midwest plains, the majestic Rockies, the desert Southwest, and finally the Pacific coast. It's a long journey, but entirely achievable within the grasp of human endeavour. Even the Earth's circumference, around 40,075 kilometres at the equator, feels conceptually manageable. Early explorers circumnavigated the globe, taking months or even years, like Ferdinand Magellan's 3-year expedition. Modern flights can do it in about 45 hours. Our Earth, for all its majesty, is a finite, comprehensible thing. Now let's leave our blue marble behind. The distance from Earth to the Moon is approximately 384,000 kilometres. Here's where conventional measurements start to feel inadequate, almost like a whisper in a hurricane. 384,000 kilometres. How do you meaningfully visualise that it's not a cross-country drive nor a leisurely sail around the world? There are no roads to follow, no landmarks to pass, no rest stops. It's pure empty space. How could you even begin to travel that far? The Apollo astronauts, using some of the most powerful rockets ever conceived, rocketed towards the Moon at about 11 kilometres per second, roughly 39,600 kilometres per hour. That's over 400 times faster than a car on a highway. Think about that for a moment, 400 times faster than you've ever driven. And even at that astounding, unprecedented speed, it took them 3 days. 3 days of relentless travel through the void just to reach our nearest celestial neighbour. The Moon is so close you can see it with your naked eye, pick out details with a pair of binoculars. It hangs there familiar in our night sky. Yet it required 3 days of rocket-powered transit. When we start talking about other planets, the Sun or distant stars' kilometres become utterly meaningless. The numbers explode, losing all intuitive connection. They become abstract symbols on a page, not distances your mind can grasp. The Earth to the Sun, around 150 million kilometres. Try to picture that. Your brain can't, can it? It's just a really big number. Nothing in our daily lives, nothing in our evolutionary history prepares us for such immensities. Even the fastest spacecraft ever built, the Parker Solar Probe, which can reach blistering speeds of up to 192 kilometers per second near the Sun, still takes months to complete its orbits. And that's our local star, the source of all life-giving light and warmth. This is why astronomers desperately needed a different unit of measure. Not because they enjoy making things complicated or baffling the public with massive figures, but because kilometres simply fail when you're charting the cosmos. Using kilometres to measure stellar distances would be like measuring the distance between continents in millimetres. Technically possible, but utterly impractical. The numbers would become so unwieldy they'd cease to be distances and just become numbers. Abstract mathematical concepts divorced from any human experience. So astronomers conceived of something else, the light year. But here's the crucial point you must understand from the outset. A light year is not a measure of time. Yes, it has year in it, making it sound like time, but it is unequivocally a measure of distance. It is the distance light travels in 1 year. Why base it on light? Because light is extraordinary. It is the fastest thing in the universe. Nothing can travel faster. This isn't just a speed limit we haven't broken. It's a fundamental law of physics. The speed of light is constant, unyielding, the same everywhere in the universe. Whether you're on Earth, Mars, in a distant galaxy, or at the edge of the observable cosmos, light always moves at the same incredible pace, approximately 300,000 kilometers per second. Let me repeat that because it's vital. 300,000 kilometers per second. Every single second light covers 300,000 kilometers. To put that into a staggering perspective, in the time it takes you to snap your fingers, light could circle the Earth's equator about 7.5 times. In a single second, it could race from New York to Los Angeles and back approximately 37 times. This speed is almost impossible for us to visualize because nothing in our everyday experience moves even remotely close to it. The fastest commercial jet flies around 900 kilometers per hour, or about 0.25 kilometers per second. Light is over 1 million times faster. Even the Parker Solar Probe at its peak 192 kHz is still only about 0.064% the speed of light. It's moving incredibly fast by human standards, but compared to light, it's crawling. When you flip a light switch, the room seems to illuminate instantly. That's because light covers the distance from the bulb to your eyes in mere billionths of a second. No perceptible delay. But light isn't instantaneous. It just feels that way over short distances. It takes time. For example, when you gaze at the sun, you're not seeing it as it is right now. You're seeing it as it was 8 minutes and 20 seconds ago, because that's how long its light takes to reach Earth. This has a fascinating implication. If the sun were to suddenly change colour dim or even explode in this very moment, we wouldn't know for over 8 minutes. The event would have already occurred, but the light carrying that information would still be on its way to us. We'd continue to see the sun as it was not as it is. The moon is closer, so the delay is less dramatic, about 1.3 seconds. This delay famously impacted the Apollo missions. When astronauts spoke to Mission Control in Houston, each word took 1.3 seconds to reach Earth, and each reply took another 1.3 seconds to reach the moon. This created a near 3-second gap in every exchange, a subtle but persistent lag that you can hear in historical recordings. Even light, the fastest traveller, requires time to bridge the gaps in space. For centuries, most people assumed light was instantaneous. You open your eyes, you see. Simple. But in 1676, Danish astronomer Ole Rømer made a peculiar observation about Jupiter's moons. The timing of their eclipses as they vanish behind Jupiter varied depending on Earth's position in its orbit. When Earth was closer to Jupiter, the eclipses occurred earlier than predicted. When farther, they were later. Rømer correctly deduced that light took a finite amount of time to travel these different distances. While his calculation wasn't perfectly accurate, he proved light had a measurable speed. Today, thanks to lasers, atomic clocks, and sophisticated instruments, we know light's speed with extraordinary precision. It's a constant woven into the very fabric of the universe itself, not just a speed, but a fundamental property of space-time. So if light travels at 300,000 kilometers per second, how far does it go in a year? Let's do the math. 300,000 kilometers per second times 60 seconds per minute, times 60 minutes per hour, times 24 hours per day, times 365 days per year. That brings us to approximately 9.46 trillion kilometers. To be more precise, it's 9,460,730,472,580.8 kilometres. But for simplicity, we usually just say 9.46 trillion kilometres. That is 1 light year. Not a measure of time, but a measure of distance. The distance that light, the fastest thing in the universe, travels in a single year. And that is the number we will attempt to truly grasp tonight. Because to understand what a light year means, you first need to understand what a trillion really represents. We use words like million, billion and trillion casually in conversation. Government budgets in the trillions, billionaires, millions of people. But we rarely truly appreciate the colossal difference between these figures. They all just sound big, but they are profoundly different. A million is 1,000 thousands. If you saved $1 every single day starting today, it would take you about 2,240 years to accumulate $1 million. That's a long time, but still comprehensible. It takes you back to ancient Greece, the early Roman Republic. A billion is 1,000 millions. Now we're multiplying by another 1,000. If you saved $1 every second, not every day, but every second, it would take you about 32 years to save $1 billion. That's more than a generation. If you started counting seconds from birth without sleep or rest, you'd be 32 years old when you reached 1 billion. 1 million seconds is about 11.5 days. 1 billion seconds is 32 years. The leap is staggering. And a trillion is 1,000 billions. This is where the numbers completely lose connection with anything relatable. If you tried to count to 1 trillion, counting one number every second without stopping, it would take you approximately 31,700 years. Let me put that in another perspective that's longer than the entire recorded history of humanity: agriculture. The very foundation of civilization was only invented about 10,000 years ago. Before that, all humans lived as hunter-gatherers. Written language appeared roughly 5,000 years ago. The Egyptian pyramids were built about 4,600 years ago. The wheel was likely invented around 5,500 years ago. To count to 1 trillion, you would have to start before any of that happened. You would have to begin when humans were still living in small tribal groups, when there were no cities, no nations, no written languages, no agriculture, no permanent settlements. You would count through the entirety of human civilization, every invention, every discovery, every empire that rose and fell, every war, every peace, every triumph and tragedy in our species' long story. And you'd still be counting today with thousands of years left to go before you reached 1 trillion. 700 years ago, modern humans were living through the last ice age. We were using stone tools, hunting woolly mammoths, and just beginning to spread across the globe. That's the span of time 1 trillion seconds takes you back, and 1 light year is 9.46 trillion kilometres. Each of those kilometres is a kilometre, a real distance you can walk in 10-12 minutes. There are 9.46 trillion distinct individual kilometre-long segments in a light year. So when we say a light year is 9.46 trillion kilometres, we're talking about a distance that dwarfs everything in our daily experience. You can write it down, calculate with it, use it in equations, but grasping it intuitively is almost impossible. Our brains simply didn't evolve to process such vast numbers. The best way to truly grasp a light year is to build it up incrementally, moving from the familiar to the utterly alien. Let's embark on this cosmic journey slowly watching, as distances that once seemed immense shrink to insignificance against the scale of what's to come. First, a light second. That's 300,000 kilometres. It's the distance from the Earth to the Moon, and about 3/4 of the way back. Think about that. In a single second, light leaves Earth, travels all the way to the Moon. 384,000 kilometers bounces back and covers most of the return journey in just 1 second. That 1.3 second communication delay between Apollo astronauts on the Moon and mission control, it's because even radio signals travelling at light speed needed that precious time to bridge the vast gap. Next, a light minute, 60 light seconds, or 18 million kilometres. The Sun is about 8 light minutes from Earth, meaning that tiny fraction of the journey from Earth to Sun is already 150 million kilometres. If you could stand on the sun, which obviously you can't, you would see Earth as it was 8 minutes and 20 seconds ago. If Earth were to suddenly vanish, you wouldn't know for over 8 minutes. This has profound practical implications for space exploration. When NASA operates rovers on Mars, there's always a communication delay. At its closest, Mars is about 32 million kilometers from Earth, roughly 2 light minutes. At its farthest, when on opposite sides of the Sun, the distance stretches to 400 million kilometers, about 22 light minutes. This means a command sent to the Perseverance rover on Mars takes anywhere from 2 to 22 minutes to arrive, and any data it sends back takes the same amount of time. You can't drive a Mars rover in real time. Instead, engineers painstakingly plan its activities, analyze images from previous days, write a sequence of commands, send them, and then wait. If something goes wrong, they can't react instantly. A problem that might take seconds to resolve with a remote-controlled car on Earth can take an hour or more to address on Mars. An hour of light is 60 light minutes, or about 1.8 billion kilometers. Over 1 billion kilometers. That's a distance so immense it's hard to even imagine. Saturn, one of the farthest planets visible to the naked eye from Earth, is about 1.2 light hours away at its closest. When the Cassini spacecraft orbited Saturn for over a decade, sending back breathtaking images and data, there was more than an hour's delay between it taking a picture and that picture arriving on Earth. Cassini couldn't be piloted in real time. Engineers had to program entire sequences of commands days or weeks in advance, upload them, and trust Cassini to execute them flawlessly. If something went wrong, the spacecraft had to be intelligent enough to handle it autonomously, recognize the problem, and enter a safe mode. Because by the time the issue was reported back to Earth, a new command sent over 2 hours would have elapsed. The situation could have entirely changed. A light day is 24 light hours, approximately 25.9 billion kilometers. We're now talking about distances where even our fastest spacecraft crawl. Voyager 1 launched in 1977 and currently the most distant human-made object from Earth is about 24 light hours away as of 2025. It's been travelling for nearly 50 years at speeds around 17 kilometers per second, incredibly fast by any human standard. Yet after 5 decades of continuous movement in the vacuum of space, Voyager still hasn't travelled a full light day from Earth. This approximate distance marks the heliopause, the boundary where the Sun's influence diminishes and interstellar space truly begins. Voyager 1 crossed this frontier in 2012, making history. But even in interstellar space, it remains within a single light day of the Sun. Cosmically speaking, right here in our cosmic backyard. A light week is 7 light days, roughly 181 billion kilometers. We are now in territory no human-made object has ever reached and won't for decades or centuries to come. Here, the Sun would no longer dominate the sky as an overwhelming source of light and heat. It would appear as a bright star, certainly brighter than others, but just one point of light in the profound darkness. A light month is approximately 30 light days, about 778 billion kilometers. At this distance, if you were to look back at the Sun through a telescope, it would appear as just another star not significantly brighter than many others. Our entire solar system, all the planets, moons, asteroids and comets, would be compressed into a tiny region around that normal star. Everything we consider our solar system, all the worlds we've studied and sent probes to, would be barely perceptible, lost in the glare of a distant sun. And finally a light year. That's 365 light days, 12 light months, 52 light weeks, 8 7 to 60 light hours, 5 to 25, 600 light minutes, or 31 5 36 Walder light seconds. See how quickly the numbers balloon. We started with a light second, already a colossal distance by human standards, and multiplied it by progressively larger numbers. And now we arrive at 1 light year, 9.46 trillion kilometers. This is the fundamental unit astronomers use to measure distances between stars, because stars are separated by light years. Nothing smaller makes sense when you're grappling with these vast cosmic scales. Why light years? Because every other option is worse. Imagine if astronomers used kilometers for everything. Proxima Centauri, Our nearest stellar neighbour is approximately 40,140 billion kilometres away. That number is awkward, hard to remember, and gives you no intuitive feel for the distance. But if I tell you Proxima Centauri is 4.24 light-years away, it's neat. You can compare it to other distances. If one star is 4 light-years and another is 40 light-years, you immediately know the second is 10 times farther. Light-years also usefully connect distance and time. When you look at a star 4 light-years away, you're seeing light that left 4 years ago. You are literally looking into the past. This connection becomes profoundly important when studying the universe. The speed of light isn't just fast, it's the universe's ultimate speed limit. Nothing, absolutely nothing, can travel faster. This isn't a technological hurdle we might one day overcome with better engineering. It's a fundamental law of physics. Albert Einstein's theory of special relativity, published in 1905, demonstrated that as objects approach the speed of light, bizarre phenomena occur. These aren't mere theoretical predictions. They're observed realities confirmed by countless experiments over the past century. Time itself slows down for the moving object, relative to stationary observers, an effect called time dilation, which has been directly measured. The object's mass, or more precisely its inertia, increases, making it progressively harder to accelerate. The energy required to accelerate it approaches infinity as you near the speed of light. To truly reach light speed would require infinite energy, which is impossible. Therefore, nothing with mass can ever reach the speed of light. Let me illustrate why this happens. In our everyday experience, if you're on a train moving at 50 km/h and throw a ball forward at 20 km/h, relative to the train, an observer on the ground sees the ball moving at 70 km/h. Speeds simply add up. This seems obvious and works perfectly for everyday velocities. But Einstein showed this simple addition breaks down at speeds approaching that of light. If you were on a spaceship moving at half the speed of light and shone a flashlight forward, you might think the light would travel at 1.5 times the speed of light from an external observer's perspective. But it doesn't. The light still travels at exactly the speed of light, 300,000 kilometers, both from your perspective on the ship and from the external observer's perspective. This seems impossible. How can light travel at the same speed for both observers when one is already moving at half the speed of light? The answer is that space and time adjust themselves to keep the speed of light constant. If you're moving very fast, time literally slows down for you from the stationary observer's viewpoint, and distances in your direction of motion actually contract. These aren't optical illusions, they are real physical effects. Time and space are not absolute, they are relative depending on your motion. The only thing that is absolute, the same for everyone regardless of how they are moving, is the speed of light. This has been experimentally verified countless times. Particles in particle accelerators moving at 99.9%. The speed of light lives significantly longer than identical particles at rest. Time literally slows down for them. This isn't theory, it's measured fact. GPS satellites orbiting Earth move fast enough and are far enough from Earth's gravity well that time dilation becomes measurable. The atomic clocks on GPS satellites run at slightly different rates than identical clocks on the ground. If GPS didn't account for this time dilation, your GPS navigation would be off by several kilometers in just a few hours. The very functionality of GPS is a testament to the reality of time dilation. Only massless particles like photons, the particles of light, can travel at the speed of light. Photons have no rest mass, so they don't need infinite energy to reach light speed. In fact, photons must always travel at the speed of light. They cannot slow down or speed up. From the moment they are created to the moment they are absorbed, they travel at exactly the speed of light. No faster, no slower. This is simply what photons do. It is their nature. These profound implications extend far beyond technical challenges for space travel. Even if we developed perfect propulsion systems with access to unlimited energy, we still couldn't go faster than light. The 4.24 light-years to Proxima Centauri represents a minimum travel time of 4.24 years even in the most optimistic scenario where we could somehow accelerate a spacecraft to nearly light speed. And that's just to the very nearest star. Most destinations in space are vastly, unfathomably farther. Some science fiction suggests ways around this limit warp drives that bend space-time around a vessel, allowing it to travel faster than light through space without actually moving faster than light in space. Wormholes that create shortcuts through space-time connecting distant points. Hyperspace and alternate dimension, where different physical laws might apply, making faster than light travel possible. These are creative ideas, and some, like the warp drive, have theoretical grounding in physics. The Alcubierre drive, proposed in 1994, is a theoretical solution to Einstein's field equations that would allow faster than light travel by contracting space in front of the craft and expanding it behind. But there are immense problems. The Alcubierre drive would require exotic matter with negative energy density, something not known to exist, and perhaps fundamentally impossible. Even if it did exist, you'd need gargantuan amounts of it, possibly more mass energy than exists in the entire observable universe. And there are causality issues. If you can go faster than light, you could potentially travel backward in time, creating paradoxes. Wormholes, if they exist, would likely be incredibly unstable, collapsing before anything could pass through. Keeping one open long enough might again require more energy than the entire universe contains, and again, causality issues abound. Hyperspace is purely speculative with no known basis in physics. It's a sci-fi concept that makes for good stories, but has no connection to real physics or mathematics. From what we understand, based on over a century of meticulous experiments and observations, the speed of light is an absolute barrier. It's not a challenge to be overcome with better technology. It's a fundamental law of nature. When we speak of stars hundreds or thousands of light years away, we're talking about distances that are fundamentally unreachable by any technology consistent with the laws of physics as we understand them. A light year doesn't just measure distance. It measures a barrier, a limit, a frontier beyond which the ordinary rules of cause and effect begin to break down for any physical interaction. Let's talk about Proxima Centauri again, because as our closest stellar neighbour, it grounds these distances in a practical reality. Proxima Centauri is a small red dwarf star, part of the Alpha Centauri triple star system. Alpha Centauri A and B are sun-like stars orbiting each other, while Proxima is much smaller, about 1/8 the mass of our Sun and 1/7 its diameter. It's so small and dim you can't see it with the naked eye despite being our closest stellar neighbour. You need a telescope to find it. Red dwarfs like Proxima Centauri are the most common type of star in our galaxy, making up about 70% of all stars, yet they're all too faint to be seen without aid. Every star you can see with your naked eye in the night sky is either larger and brighter than our Sun, or it's not a star at all but a planet. Proxima Centauri is 4.24 light-years away. That's approximately 40,140 billion kilometers, a 40 followed by 12 zeros. To put this in perspective, if you could travel at the top speed of the fastest spacecraft ever built, the Parker Solar Probe at 192 kilojouless, it would take you about 6,800 years to reach Proxima Centauri. That's longer than the entire recorded history of humanity. You could have started your journey when humans first learned to write, travelling non-stop, at the fastest speed any human spacecraft has ever achieved, and you'd still be moving today with thousands of years left until you reached your destination. There have been proposals for faster spacecraft. The Breakthrough Starshot initiative, announced in 2016 by Stephen Hawking and Yuri Milner, suggests using powerful ground-based lasers to accelerate tiny spacecraft to about 20% the speed of light. The concept is elegant and scientifically plausible, at least in principle. You build a spacecraft that's essentially a computer chip with a camera weighing perhaps just a gram, attached to an ultra-thin light sail made of reflective material just a few atoms thick. Then you aim massive arrays of lasers at it from Earth. The laser light pushes the sail, and because the spacecraft is incredibly light, it could accelerate to immense speeds. At 20% the speed of light, about 60,000 kilometers, a probe could reach Proxima Centauri in approximately 20 years. Add another 4 years for the signals to travel back to Earth at light speed, and you could receive data from Proxima Centauri within 24 years of launch. That's within a human lifetime, which is genuinely exciting. You could launch a mission in your youth and see the results before you die. But the technical challenges are monumental, perhaps insurmountable with current or near-future technology. First, you need incredibly powerful lasers. The proposal calls for a laser array with a total power of about 100 gigawatts, roughly the output of 100 nuclear power plants, all focused into a laser beam several kilometers wide. This beam would need to track the tiny spacecraft as it accelerates, keeping the light precisely focused on the sail. Any deviation and the sail drift out of the beam and acceleration stops. Second, the spacecraft needs to survive the journey. At 20% the speed of light you're moving at 60,000 km/s. At this speed, colliding with even tiny particles becomes catastrophic. A dust grain smaller than a speck of sand hitting the spacecraft at this velocity would release energy equivalent to a large bomb. The spacecraft would need shielding, but any shielding adds weight, and weight is the enemy when trying to accelerate something with light pressure. The heavier the craft, the more energy you need to accelerate it, and the equations worsen as you add weight. Third, you need to be able to communicate with the spacecraft across 4 light years. The tiny probe would need a laser or radio transmitter powerful enough to send data back to Earth from 4.24 light years away. At that distance, any signal spreads out enormously. The energy required to send a detectable signal is substantial, and you have to integrate this capability into a spacecraft the size of a computer chip. It's like trying to shout across an ocean and be heard clearly on the other side. Fourth, you need to actually fly into the Proxima Centauri star system and pass through it at the right distance and angle to gather useful data. At 20% the speed of light, the spacecraft moves so fast that it crosses Mars's orbit in about 40 minutes. The entire width of our solar system from the Sun to Neptune is traversed in about 6 hours. You get one chance. There's no slowing down, no course corrections once you've reached speed, because decelerating requires as much energy as accelerating. The spacecraft would flash past Proxima Centauri at 60,000 kilometers AE, having perhaps a few hours or at most a couple of days when it's close enough to take useful pictures and measurements, then continuing its journey into the void, never to be seen again, drifting through interstellar space forever. So while Breakthrough Starshot is a fascinating concept based on real physics, it remains highly theoretical. The technology doesn't yet exist, and the challenges are immense. Even if we could build such a craft and successfully launch it tomorrow, it would still take at least 20 years for it to reach Proxima Centauri, and another 4 years before we received any data. That's a 24-year round trip for information, assuming everything works perfectly, which in the history of space exploration is never a safe assumption. And this is just to reach our nearest stellar neighbour. With the technology we can actually build today, the kind of spacecraft we know how to design and launch, with current rockets, materials and computer systems, reaching Proxima Centauri would not take decades but millennia. We would need to build multi-generational starships, colossal vessels capable of sustaining crews for thousands of years. The people who arrived at Proxima Centauri would be distant descendants of those who launched perhaps hundreds of generations removed, having lived their entire lives in a world they'd never left travelling toward a destination they'd only heard about in stories passed down through centuries. When you look up at the night sky, you're seeing stars at different distances, and you're seeing them as they were years or even centuries ago. This is one of the most profound implications of the light year. Distance and time become inextricably linked. You cannot separate where an object is from when you see it. Light travels at a finite speed. It's incredibly fast but not instantaneous. When light leaves a star and travels through space towards Earth, that journey takes time, and in that time anything can change. The star might dim, change colour, or even explode. By the time its light reaches your eyes, the star you're seeing might be completely different from its current state. Or it might not even exist anymore. Sirius, the brightest star in our night sky, is 8.6 light-years away. When you look at Sirius tonight, you're seeing light that left that star 8.6 years ago. You are looking at Sirius as it was when you were 8.6 years younger. If you're 20 years old, you're seeing Sirius as it was when you were about 11 perhaps in middle school. Sirius tonight is Sirius from the past, not Sirius as it exists in this very present moment. Of course, Sirius is a stable main sequence star. It won't change much in a few years or even decades. Stars change very slowly from a human perspective over millions or billions of years, not years or decades. But the principle is what's important here. You don't see Sirius as it is, you see Sirius as it was. You are looking back in time every single time you look at a star. Vega is another bright star about 25 light years away. If you are 25 years old and you look at Vega tonight, you're seeing light that left that star in the year you were born. When that light began its journey towards Earth, you didn't exist. Your parents might have looked up at that same star seeing light that had left Vega 25 years before that, a total of 50 years ago. The Vega you see tonight is a younger Vega showing you what that star looked like a quarter century ago, not what it's doing right now. Betelgeuse, the red supergiant in the constellation Orion, is about 550 light-years away. It's one of the most famous stars in the night sky, easily visible as the bright orange-red star marking Orion's shoulder. The light you see from Betelgeuse tonight began its journey towards Earth in 1474, during the Italian Renaissance before Columbus sailed to the Americas, when Leonardo da Vinci was 22 and Michelangelo was about to be born. In 1474, the Byzantine Empire had fallen 21 years prior. The printing press had only just been invented around 20 years earlier. Most of Europe was still emerging from the Middle Ages. The modern world as we know it simply did not exist. And the light from Betelgeuse you see tonight began its journey then. It has travelled through space for over 500 years, traversing the vast darkness between Betelgeuse and Earth to reach your eyes tonight. Betelgeuse is a particularly intriguing example because it's a massive star nearing the end of its life. Stars like Betelgeuse don't last as long as smaller stars like our Sun. They burn through their fuel much faster. At some point in the relatively near future in astronomical terms, within the next 100,000 years, Betelgeuse will explode as a supernova. When it does, it will temporarily blaze as brilliantly as a full moon in our sky, visible even in broad daylight. It will be a spectacular event, one of the most impressive astronomical occurrences visible from Earth in human history. But here's the thing, Betelgeuse might have already exploded. The explosion might have happened centuries ago. Perhaps it went supernova in the 1600s or 1700s or 1800s. But we wouldn't know yet. We'd have no way of knowing. The light from that explosion would still be travelling towards us through space, moving at light speed, taking 550 years to complete its journey. So if Betelgeuse exploded in 1700, we wouldn't see it until around the year 2250. That star might be gone right now, utterly destroyed in a cataclysmic supernova, and we would still see it shining peacefully in our sky for centuries to come, completely unaware that we are seeing a ghost, an image of something that no longer exists. Polaris the North Star is about 445 light-years away. When its current light began its journey to us, the first permanent English colonies in North America hadn't even been established. Jamestown wouldn't be founded for another 12 years. The Pilgrims wouldn't reach Plymouth Rock for another 26 years. William Shakespeare had just begun writing his plays. The United States wouldn't exist for another 180 years. When the light from Polaris began its journey, the world was utterly different from today. And tonight that ancient light enters your eyes. You're connected across space and time by photons that have travelled for 4.5 centuries. Within about 20 light-years of Earth, there are roughly 130 known star systems. Some are single stars like our Sun, others are binary systems with 2 stars orbiting each other, or even triple star systems like Alpha Centauri. Understanding this stellar neighbourhood helps us appreciate both the distances involved and the diversity of stars that exist in our cosmic backyard. Barnard's star, for instance, is the second closest star system to Earth, after Alpha Centauri about 6 light-years away. It's a red dwarf much smaller and dimmer than the Sun. What makes Barnard's star particularly interesting is that it's moving towards us relatively quickly, by stellar standards. It has the largest proper motion of any known star, meaning it moves across the sky faster than any other star when viewed from Earth. Over decades and centuries, we can actually see Barnard's star shift its position relative to other stars. In about 10,000 years, it will be closer to Earth than Proxima Centauri is now becoming our new closest stellar neighbour. But even at its closest approach, it will still be nearly 4 light-years away. The distances between stars are so vast that even when stars are hurtling towards each other, it takes thousands or tens of thousands of years for that motion to make a significant difference in their separation. Our Milky Way galaxy is a spiral galaxy containing anywhere from 100 billion to 400 billion stars. That's a huge range because it's incredibly difficult to count stars when you're inside the galaxy, like trying to count trees while standing in the middle of a dense forest. Dust blocks our view in many directions, dim stars are hard to detect, and the galaxy is simply too vast for us to see all at once from our vantage point. But best estimates suggest around 200 to 300 billion. Our Sun is just one of these, an average yellow dwarf star of moderate size and brightness. There is nothing particularly special about our Sun from a galactic perspective. It's not the biggest, brightest, hottest, or coldest. It's just a typical star one among hundreds of billions, and it resides in one of the spiral arms about 26,000 light-years from the galactic centre. 26,000 light-years. The light we see from the very centre of our galaxy, if we could peer through all the obscuring dust, left the galactic core 26,000 years ago. When that light began its journey, humans were still living as hunter-gatherers in the Stone Age. Agriculture hadn't been invented. There were no permanent settlements, no cities, no civilizations as we understand them. Humans lived in small nomadic groups, following animal herds, gathering wild plants using simple stone tools. Written language wouldn't be invented for another 21,000 years. Everything we consider human civilization, from the first farms to the first cities to the first writings, to all the ancient empires to the modern world, all of it unfolded while that light from the galactic centre was travelling to us. And that light which left when humans were still primitive hunter-gatherers reaches Earth tonight. The Milky Way galaxy is approximately 100,000 light-years across from one edge of its spiral arms to the other. If you could somehow travel at the speed of light, which you can't, it would take you 100,000 years to traverse the galaxy from one side to the other. 100,000 years. Modern humans. Homo sapiens are about 300,000 years old as a species. So you could have begun traversing the galaxy when the very first modern humans appeared in Africa, travelled at the speed of light for 100,000 years, and you would only be 1/3 of the way across the galaxy today. Our Sun orbits the galactic centre at about 230 kilometres. That sounds fast, and it is. At that speed you could cross the continental United States in about 3 minutes. You could circle the Earth in less than 3 minutes. But even at this incredible velocity, it takes the Sun about 225 to 250 million years to complete one full revolution around the galaxy. The last time the Sun was in its current position in the galaxy, dinosaurs were just beginning to evolve on Earth. Since then, dinosaurs evolved, dominated Earth for over 160 million years, went extinct. 66 million years ago, mammals took over and humans eventually evolved, and the Sun has only just returned to nearly the same spot in the galaxy it was when dinosaurs first appeared. One of the most exciting developments in astronomy over the last few decades has been the discovery of exoplanets, planets, orbiting stars other than our Sun. Until 1992, we knew of only one planetary system, our own solar system. We suspected other stars might have planets, but we had no direct proof. Then, in 1992, astronomers found the first planets orbiting another star, a pulsar. In 1995, they found the first exoplanet orbiting a normal Sun-like star, and since then the discoveries have exploded. As of 2024, we've confirmed the existence of over 5,000 exoplanets, with thousands more candidates awaiting verification. The TRAPPIST-1 system, located about 40 light-years away, contains 7 Earth-sized planets, orbiting a small red dwarf star. 3 of these planets lie within the habitable zone, where temperatures could allow liquid water to exist on the surface. This discovery, announced in 2017, was revolutionary for several reasons. It showed that small red dwarf stars could host multiple rocky planets. Since red dwarfs are the most common type of star in the galaxy, this suggests that rocky planets could be incredibly common throughout the universe. The TRAPPIST-1 system is also remarkable because the planets are tightly packed together. All 7 planets orbit their star closer than Mercury orbits our Sun. But because the star is so small and cool, 3 of the planets receive comparable amounts of energy from their star as Earth does from the Sun. If you stood on one of these planets, you'd see the other planets in the sky, some appearing larger than our Moon does from Earth. The planets are so close that travelling between them would be far easier than moving between planets in our own solar system. When we observe the TRAPPIST-1 system today, we're seeing it as it was 40 years ago in 1985. If there is intelligent life on one of those planets, and if that life developed radio technology and began broadcasting signals into space, those signals would take 40 years to reach us. We would receive a signal today that was broadcast in 1985, and if we detected such a signal today and sent a reply, it would take another 40 years for our reply to reach them. They would receive our answer in 2065. That's an 80-year round trip for a single exchange of information. You could ask a question and die of old age before you ever received an answer. Think about the implications of communication when distances are measured in light years. This is one of the most challenging and sobering aspects of cosmic scale, and it has profound implications for any future humanity might try to establish settlements on other worlds or communicate with extraterrestrial civilizations. Radio waves travel at the speed of light. They're electromagnetic radiation just like visible light but with longer wavelengths. When we send radio signals into space, they spread outwards in all directions at 300,000 km/s. But even at this incredible speed, the fastest possible in the universe communicating across light years takes years. Voyager 1, our most distant spacecraft, is currently about 24 light hours from Earth. That means there's a communication delay of roughly 24 hours each way. When mission controllers on Earth send a command to Voyager, that command takes about 24 hours to reach the spacecraft. Any data Voyager sends back takes another 24 hours to reach Earth. There's approximately a 48-hour lag for any two-way communication. If something goes wrong with the spacecraft, if a system malfunctions or an anomaly occurs, Voyager has to handle it itself. By the time engineers on Earth even know there's a problem and send new commands to address it, 2 full days have passed. The situation could have completely changed in that time. The New Horizons spacecraft, which flew past Pluto in July 2015, was about 4.5 light hours from Earth during the flyby. All the data it collected during those precious few hours near Pluto had to be stored on board, then transmitted back to Earth over the subsequent months. Each sequence of commands had to be programmed weeks or months in advance. Mission controllers couldn't react to what the spacecraft was seeing in real time. They had to plan everything perfectly, anticipate every possible scenario, and trust the spacecraft to execute its mission autonomously. Now imagine trying to establish communication with a human settlement on a planet orbiting Proxima Centauri 4. 24 light years away. You send a message asking how things are going, how the crops are growing, whether there are any issues that need addressing. That message travels at light speed for 4.24 years. 4 years, 2 months, and about 20 days later, your message arrives. If they respond immediately, writing their reply and sending it right back, their answer takes another 4.24 years to reach you. That's over 8 years for a single exchange of information. You could ask about their latest harvest and receive an answer about crops that were eaten 4 years ago. You could inquire about the health of a sick loved one and receive news of their death years after it occurred. You could send advice or aid, but by the time it arrived, the situation would have utterly transformed. Any kind of real-time communication, the kind of instant back-and-forth conversation we take for granted, is utterly impossible across these distances. Conversations would be painfully, frustratingly slow. Debates would stretch for decades. A diplomatic negotiation between Earth and a Proxima colony could take a century or more to resolve, with each side having to carefully consider its responses, knowing that years would pass before hearing back, and many more years before their answer could be reciprocated. This has profound implications for governance and society that go far beyond mere inconvenience. A colony 4 light-years away cannot be governed from Earth in any meaningful sense. Any laws or directives sent from Earth would arrive years out of date. The political situation on Earth could completely change between the time a message is sent and the time it arrives. By the time the colony received orders from Earth, those orders could be obsolete, overthrown by new governments or new policies. The colony would need to be self-governing, capable of making its own decisions on everything from resource allocation to conflict resolution to emergency response. Because waiting years for approval or guidance on every decision would be impossible. The colony and Earth would gradually drift apart culturally over time, developing their own customs, ways of life, and solutions to problems. They would be connected by messages from the past letters from another time, but unable to maintain the kind of instant, continuous connection that binds societies together. Over generations, they might become so different as to be almost unrecognizable to each other. For stars farther away, it's even worse. A settlement 10 light-years away would have a 20-year round-trip communication time. Messages you sent to your children living there would reach them as adults, perhaps, with children of their own. Their replies would come back when your grandchildren were grown, when you were elderly or possibly even deceased. You would be exchanging correspondence across decades like messages from different eras. You could share news and stay in touch in some abstract sense, but you could not have a relationship in any normal meaning of the word. A civilization 100 light-years away would have a 200-year communication delay. You could send a message and neither you, your children, your grandchildren, or even your great-grandchildren would live to see the reply. Only your great-great-grandchildren living in a world you could barely imagine might hear back from that distant civilization. The conversation would span generations, with each generation sending messages to strangers. They would never meet people separated not just by distance, but by time receiving messages from those long dead. If you could travel at speeds close to light, something very strange would happen to time. This is Einstein's time dilation, and it has been confirmed by countless experiments. It's not speculation. It's an observed fact as firmly established as gravity or electromagnetism. As you approach the speed of light, time slows down for you relative to stationary observers. The faster you go, the more extreme this becomes. This isn't just your clock running slow, it's time itself slowing down. Your heartbeat, your thoughts, your aging process, your metabolism, everything unfolds more slowly from the perspective of someone not moving with you. Although from your own perspective, sitting in your spacecraft, everything seems perfectly normal. Time passes normally for you. It's everyone else's time that seems to speed by. Imagine a spacecraft that could somehow reach 99.9% the speed of light. Not quite light speed, but very close. You board this ship and travel to a star 10 light-years away, then return. From Earth's perspective, this journey would take just over 20 years, 10.1 years to get there at 99.9% C, and another 10.1 years to return. Anyone observing from Earth would see your spacecraft take roughly 20 years for the round trip. But because of time dilation, you would age far less. At 99.9%, the speed of light time passes about 22 times slower for you than for those on Earth. So while 20 years passed on Earth, you would only experience about 11 months. You would step off the spacecraft having aged less than a year, while everyone you knew had aged 20 years. Your siblings might now be older than you. Your children, if you had any, might now be grown adults older than you. You would have travelled into their future. If you travelled even faster at 99.99% the speed of light, you could travel to a star 100 light-years away and back. From Earth's perspective, this journey would take over 200 years. But from your perspective, due to the extreme time dilation at this speed, the journey might only take a few years of your life. You would experience a few years of travel time living through those few years on the spacecraft. But when you return to Earth, over 200 years would have passed. Everyone you knew would be long dead. The world would be utterly different. Political systems would have changed. Technology would have advanced. Language might have evolved. You would return to a future Earth that would be as alien to you as if you had travelled to a different planet. Let's zoom out further. The observable universe is the region of space from which light has had time to reach us since the Big Bang. The universe is about 13.8 billion years old. Light has been travelling towards us for that entire duration, but the observable universe is larger than 13.8 billion light years because the universe has been expanding while the light has been travelling towards us. The observable universe has a radius of about 46.5 billion light years, making it roughly 93 billion light years across. This is the distance to the edge of what we can possibly see. Beyond this distance, space has expanded so rapidly that light from those regions hasn't had time to reach us, and never will. There's a cosmic horizon we cannot see, not because we don't have powerful enough telescopes, but because the light simply hasn't had time to reach us, given the age of the universe and the rate of its expansion. Within this observable universe, it's estimated there are 2 trillion galaxies. Each galaxy contains billions or even trillions of stars. If you multiply that out, the total number of stars in the observable universe is estimated to be around 200 sextillion. That's a 2 followed by 23 zeros, and we know from observations that most stars have at least one planet orbiting them. So there are likely a similar or even greater number of planets. The universe is teeming with worlds. More worlds than we can count. More worlds than we could possibly visit even with unlimited time and technology. At the larger scales, the universe has structure. Galaxies aren't randomly sprinkled in space like grains of sand. They are organised into clusters, groups of galaxies held together by gravity. These clusters are organised into superclusters, enormous structures containing many galaxy clusters. And superclusters are arranged into filaments, gigantic thread-like structures stretching for hundreds of millions of light years through space. Between these filaments are vast voids regions with very few galaxies, empty spaces that can be hundreds of millions of light years across. The universe is expanding. Space itself is stretching, carrying the galaxies along like raisins in rising dough. This isn't just galaxies moving through space. Space itself is expanding, creating more space between distant objects. For nearby objects, this expansion is negligible, overridden by other forces. The space between Earth and the Moon isn't expanding in any meaningful way. Gravity holds Earth and the Moon together. The space within our solar system isn't expanding. Gravity holds the planets in their orbits. The space within our galaxy isn't expanding. Gravity holds the stars together in the Milky Way. But at larger scales, between galaxies and especially between clusters of galaxies separated by hundreds of millions or billions of light years, the expansion becomes significant and eventually dominates. Distant galaxies are receding from us as space expands between us and them. The farther away a galaxy is, the faster it recedes. This isn't because the galaxies themselves are moving through space at high speeds. They're relatively stationary within their local regions of space, but the space between us and them is expanding, and that expansion accumulates over vast distances, adding up to high recession velocities. For galaxies far enough away, the space between us and them is expanding faster than light can travel through it. This doesn't violate the cosmic speed limit because the galaxies themselves aren't moving faster than light through space. They are essentially stationary in their local space, but space itself is expanding so fast that the distance between us increases faster than light can bridge the gap. It's like trying to walk forward on a treadmill that's running backward faster than you can walk forward. You're walking at a normal speed, but you're moving backward relative to your starting point, because the treadmill is moving faster than your walking speed. This means there are regions of the universe that are moving away from us so fast that light from those regions will never reach us. Not in a billion years, not in a trillion years, never. There's a cosmic horizon we cannot see, not because the light hasn't had time to reach us, but because it will never reach us. The expansion of space is carrying those regions away faster than their light can close the distance. We are fundamentally irreversibly cut off from those regions of the universe. So what does all this mean for us? How should we think about the light year in our daily lives? For most people, the light year doesn't impact everyday existence. You don't need to consider Proxima Centauri's 4.24 light-year distance when deciding what to eat for breakfast, whether to bring an umbrella or which route to take to work. but there is profound value in occasionally stepping back and contemplating these scales. It provides perspective on our place in the universe. When you realise that Earth is a tiny planet orbiting an ordinary star, and the next closest star is over 4 light-years away, and our galaxy contains hundreds of billions of stars, and there are trillions of galaxies in the observable universe, it changes how you see everything. Your problems, whatever they may be, exist on a tiny planet in a vast cosmos. That argument with a friend, the pressure at work, worries about the future, frustrations, annoyances, all unfold in a small world. The nearest star doesn't care about your problems. The galaxy pays no heed. The universe continues its slow, majestic evolution, utterly indifferent to human affairs. This isn't meant to diminish your experience or suggest your problems aren't important. Your life matters to you, and that is what matters. Pain is pain. Joy is joy. Love is love. These things are real and important regardless of the universe's scale. But sometimes when things feel overwhelming, when you are stressed or anxious or wondering, recalling the scale of the universe can be helpful. It can help you remember that you are living on a small planet, orbiting an ordinary star in a vast universe. And from that cosmic perspective, your problems are temporary, localized, tiny, not unimportant, but tiny, containable, manageable. There is also something beautiful in understanding the light year. When you look up at the night sky, you're not just seeing bright dots. You're seeing stars that are light years away. You're seeing photons that have travelled through space for years or centuries to reach your eyes. You're connected to those distant suns across immense gulfs of space and time. You're a part of the universe made of atoms forged in stars, looking up at other stars, understanding your place in the cosmic order. As Carl Sagan famously said, we're a way for the cosmos to know itself. Each star has a story. Some are young, just born from collapsing clouds of gas and dust, beginning their lives as nuclear furnaces. Some are middle-aged, like our sun, steadily burning hydrogen, in their cores, stable and long-lived. Some are ancient, nearing the end of their lives, having exhausted their fuel, destined to become white dwarfs, cooling over trillions of years, or exploding into supernovae, scattering their atoms across space to be recycled into new stars and planets. And all of them are separated by light years by distances so immense that even light requires years to traverse them. The universe is a sparse place with tiny islands of light separated by vast oceans of darkness. There is also something beautiful in understanding the light year. When you look up at the night sky, you're not just seeing bright dots. You're seeing stars that are light years away. You're seeing photons that have travelled through space for years or centuries to reach your eyes. You're connected to those distant suns across immense gulfs of space and time. You're a part of the universe made of atoms forged in stars, looking up at other stars, understanding your place in the cosmic order. As Carl Sagan famously said, we are a way for the cosmos to know itself. Each star has a story. Some are young, just born from collapsing clouds of gas and dust, beginning their lives as nuclear furnaces. Some are middle-aged, like our sun, steadily burning hydrogen, in their cores, stable and long-lived. Some are ancient, nearing the end of their lives, having exhausted their fuel, destined to become white dwarfs, cooling over trillions of years or exploding into supernovae, scattering their atoms across space to be recycled into new stars and planets. And all of them are separated by light years by distances so immense that even light requires years to traverse them. The universe is a sparse place with tiny islands of light separated by vast oceans of darkness. Yet those islands are connected. Connected by light, by gravity, by the fact that they are all made of the same stuff. Atoms forged in the hearts of previous stars, dispersed and recycled and reborn into new generations of stars and planets, and potentially life. As our technology improves, our ability to measure light-year distances becomes more precise. The Gaia spacecraft is creating the most accurate three-dimensional map of our galaxy ever made, measuring the positions and distances of over 1 billion stars. Future telescopes will allow us to peer even farther. The James Webb Space Telescope has already detected galaxies over 13 billion light-years away, looking back into the early universe just after the Big Bang. We're also discovering more exoplanets every year, mapping what exists at these vast distances. In the future, we may send robotic probes to nearby stars. Breakthrough Starshot proposes sending tiny spacecraft to Proxima Centauri. Even if successful, those probes would take over 4 years to send data back. But unless there are revolutionary breakthroughs in physics, the light year will remain a fundamental barrier. The distances between stars are immense and the speed of light is finite. This isn't a problem to be solved. It's a fundamental attribute of the universe we inhabit. Understanding the light year changes how we view our place in the universe, and it poses profound questions about humanity's future and our relationship to the cosmos. These aren't just abstract philosophical questions. They have practical implications for how we think about space exploration, the search for life, and the long-term future of our species. For most of human history, the universe was small. Ancient peoples thought the stars were lights attached to a celestial sphere just beyond the moon and planets. The entire cosmos was contained within a space you could almost reach if you climbed high enough. Even when we realised stars were distant suns, we had no sense of their true distances. A few million kilometres, a few billion. Those numbers were beyond our capacity to measure, so they remained abstract, indefinite. It wasn't until the early 20th century that we truly began to accurately measure stellar distances and realise just how vast space truly is. When Harlow Shapley calculated the size of the Milky Way in 1918, showing it was about 100,000 light-years across, many astronomers were shocked. The universe was far larger than anyone had imagined, and when Edwin Hubble demonstrated in 1929 that spiral nebulae were actually distant galaxies millions of light-years away, the universe suddenly expanded by many more orders of magnitude. We went from thinking the Milky Way was the entire universe to realising it was just one galaxy among potentially billions. Today we know the observable universe is 93 billion light-years across and contains an estimated 2 trillion galaxies. That's a number so large it's almost meaningless, but it represents a real physical space that exists all around us. Every direction you look, if you could see far enough, you would see galaxies stretching away into the distance, more and more galaxies, until you eventually reach the edge of the observable universe, where light simply hasn't had time to reach us. This knowledge fundamentally shifts our perspective. We're not at the centre of the universe. We're not special in any cosmic sense. We live on a typical planet orbiting a typical star in a typical galaxy, in a typical region of space. There is nothing unique about our location. If you were transported to another galaxy billions of light-years away, you would see a similar vista galaxies in every direction stretching to the horizon. The universe looks pretty much the same from every vantage point. This is both humbling and empowering. Humbling because it shows us how tiny we are in cosmic terms. The entire history of human civilization, everything we have ever done, every war fought, every empire built, every discovery made, all of it occurred on a tiny planet in a small corner of a typical galaxy. From a cosmic perspective, we are almost insignificant. We are like bacteria living in a single drop of water, utterly unaware of the ocean around us. But it is also empowering because it shows us our capability. We figured this out. We measured these distances. We understood our place in the universe. We built telescopes and spacecraft and mathematical models that allow us to see and measure things billions of light-years away. We are tiny, but we're also incredibly capable. We are conscious beings who can understand the universe that created us. That is remarkable. Understanding the light-year forces us to confront difficult truths about space exploration and humanity's future beyond Earth. The distances involved are so immense that they may represent fundamental barriers that no amount of technological progress can overcome. Consider what it would take to send humans to another star. Proxima Centauri is 4.24 light-years away. With current technology, the fastest spacecraft we've built travels at about 132 km at its peak. At that speed, it would take roughly 600 to 800 years to reach Proxima Centauri. That's longer than the entire recorded history of humanity. You could have launched your mission when humans first invented writing. And it still wouldn't have arrived. For interstellar travel to become practical, we would need to go far, far faster, even at 10% the speed of a light, which would require revolutionary new propulsion systems far beyond anything we can currently build. It would still take over 42 years to reach Proxima Centauri. That's longer than most careers, longer than the typical span from graduation to retirement, and that's just to the nearest star. Most stars are vastly farther. The technical challenges are immense. You need enormous amounts of energy to accelerate a spacecraft to these speeds. You need to shield the crew from radiation for the entire journey. You need to provide life support for decades. You need to deal with the psychological effects of being confined in a tiny spacecraft for most of your life, never seeing Earth again, travelling through empty space toward a destination you might not reach in your lifetime. Multi-generational ships have been proposed, colossal vessels that could sustain hundreds or thousands of people for centuries to reach another star. The people who arrived would be distant descendants of those who launched. They would be born on the ship, live their entire lives on the ship, and eventually arrive at a destination they only knew in stories. The ship would effectively be a small civilization travelling cut off from Earth, developing its own culture and society over the long voyage. But even multi-generational ships might not be practical. How do you maintain a closed ecosystem for centuries? How do you prevent genetic issues from inbreeding in a small population? How do you ensure the descendants still want to complete the mission their ancestors started? What if they decide after a few generations that they want to turn back and go home? What if there's a catastrophe, a system malfunction, a plague that wipes out most of the population? No rescue is coming. They are light years away from help. Some have suggested suspended animation or cryo-freezing, putting the crew to sleep for the journey and waking them when they arrive. This would solve many problems. No need for decades of life support, no psychological issues from long confinement, no generational drift in mission goals. But we don't know if that technology is even feasible. Can the human body survive being frozen for decades or centuries and then be revived? What about cellular damage from ice crystal formation? What about the effects on the brain and memory? These are all unsolved problems that may not have solutions. The reality is that interstellar travel with humans on board may simply be impractical, given the limits imposed by the speed of light and the vast distances measured in light years. We may be confined to our own solar system for the foreseeable future, perhaps permanently. That doesn't mean we can't explore other star systems with robotic probes, but human exploration of other stars may forever remain in the realm of science fiction. The light year also shapes our thinking about the possibility of communicating with alien civilizations. If intelligent life exists elsewhere in the universe, and many scientists think it likely does given the immense numbers of stars and planets, then the distances measured in light years may make communication impossible, even if both civilizations exist for millions of years. Suppose there is an advanced technological civilization on a planet orbiting a star 50 light years away. They've developed radio technology and have been broadcasting signals into space for a century just like us. Those signals are currently passing through our region of space, but they are incredibly faint after travelling 50 light years spread out over an enormous sphere. To detect them, we would need to aim very sensitive radio telescopes in precisely that direction, at the exact frequency at the right time. The chances of that happening by accident are infinitesimally small. Even if we did detect their signal, think about what happens next. We would receive a signal they broadcast 50 years ago. If we replied immediately, our response would take another 50 years to reach them. That's a 100-year round trip for a single exchange. You could ask a question and die of old age before you ever receive the answer. Your great-grandchildren might hear the answer to a question you asked. This fundamentally changes the nature of any potential contact. There can be no dialogue in any normal sense, no conversation, no real-time negotiation. Instead, it would be more like an exchange of encyclopedia entries, each civilization sending everything they know, everything about their history, science, and culture, and hoping the other civilization receives it and replies in kind. It would be more like archaeology than communication, studying records left by a distant civilization, records that are decades or centuries old by the time they arrive. and that assumes both civilizations exist long enough and remain interested in communicating long enough for this exchange to occur. Humans have only been broadcasting radio signals for about a century. We don't know if we'll still be broadcasting in another century, let alone several centuries. Civilizations might rise and fall on timescales shorter than the time light takes to travel between stars. We might detect signals from a civilization that went extinct centuries ago, listening to the radio echoes of a dead world. There's also the unsettling possibility that the universe may be teeming with civilizations, but all are too far apart for any to ever make contact. The average distance between intelligent civilizations might be thousands of light years. At such distances, even detecting each other becomes almost impossible, and communication becomes meaningless. Each civilization develops, alone makes its discoveries alone, asks its questions alone, and eventually dies alone, never knowing if anyone else was out there. One of the most profound implications of understanding the light year is realizing just how isolated we are. The distances between stars are so vast that meaningful communication or travel may simply be impossible, leaving civilizations forever isolated in their own tiny pockets of space. Even within our own galaxy, even assuming millions of technological civilizations, the average distance between them might be thousands of light years. At such distances, communication is almost meaningless. By the time you receive a message and send a reply, thousands of years have passed. The civilization that sent the original message may no longer exist. Their planet might have been destroyed by an asteroid impact. Or they might have self-destructed in a war, or their star might have become unstable and rendered their world uninhabitable. You would be sending a message to ghosts. This paints a picture of a universe that may be teeming with life, perhaps even intelligent life, but where that life is forever isolated by the vast distances of space. Each civilization develops alone, asks its questions, alone makes its discoveries alone, and eventually dies alone, never knowing if anyone else was out there, never making contact with other intelligences under other suns. There is something profoundly melancholic about this. We evolved as social creatures. Connection with others is fundamental to who we are as humans. We build communities, share knowledge, and collaborate on projects. The idea of being alone in the universe or being surrounded by others, but forever unable to reach them or meaningfully communicate with them is one of deep isolation. But there is also something beautiful about it. It means that each civilization that arises is precious. If we are alone or effectively alone because we cannot reach anyone else, then we carry a unique responsibility. We are the way the universe knows itself in this particular corner of space. The thoughts we think, the art we create, the science we discover, the love we feel, all of it is unique to us. We are not just one civilization among millions. We may be the only intelligences within dozens or hundreds of light years in any direction. This makes what we do more important, not less. Every act of kindness, every discovery, every work of art, every moment of joy or connection or understanding, all of it matters because it is happening here and now and may not be happening anywhere else nearby. We are alone, but we are also important. We are tiny, but we are also precious. We are insignificant in cosmic terms, but we are also irreplaceable, because there may be no one else like us for light years in any direction. Tonight we have taken a deep dive into the light year. We've explored what it means, how it's measured, the distances it represents, and its profound implications for understanding the universe. We've journeyed from the familiar scales of our daily lives to the almost incomprehensible scales of cosmic distance. A light year is 9.46 trillion kilometers, the distance light travels in 1 year, moving at 300,000 kilometers. It's the unit astronomers use because kilometers and other terrestrial measurements become utterly unwieldy when dealing with cosmic distances. When you're measuring distances to stars and galaxies, you need a unit large enough to make the numbers manageable, while still being based on something physical and measurable. The closest star to our Sun, Proxima Centauri, is 4.24 light-years away. That's our nearest stellar neighbour, and it's still so far that with current technology it would take thousands of years to reach it. Our galaxy, the Milky Way, is about 100,000 light-years across from one edge to the other. To cross our galaxy at the speed of light, you would need 100,000 years. The observable universe is 93 billion light-years across, containing an estimated 2 trillion galaxies each with billions or trillions of stars. When you look at the stars in the night sky, you're not seeing them as they are right now. You're seeing light that has travelled for years or centuries or even millennia to reach your eyes. You're literally looking into the past. Sirius, the brightest star in the night sky, is 8.6 light-years away. You're seeing it as it was 8.6 years ago. Betelgeuse, the red supergiant in Orion, is about 550 light-years away. You're seeing it as it was during the Renaissance over 5 centuries ago. A light-year connects distance and time in a fundamental way, showing them to be unified aspects of space-time rather than separate concepts. The speed of light is a fundamental speed limit built into the very fabric of the universe. Nothing can travel faster than light. This is not a technological limit we can overcome with better engineering. It's a law of physics, a consequence of how space-time works. This means that distances measured in light-years represent real barriers to communication and travel. Stars light-years away are separated from us not just by space but by time. Even travelling at the speed of light, which is impossible for anything with mass. You would still need years to reach nearby stars and thousands or millions of years to reach distant galaxies. The universe is expanding and that expansion is accelerating. Dark energy, a mysterious force we don't understand, is pushing the universe apart at an ever-increasing rate. Distant galaxies are receding from us as space expands between us and them. In the far future, billions of years from now, the universe will be far emptier from our perspective as more and more galaxies are pushed beyond our cosmic horizon, carried away by the expansion of space faster than their light can reach us. Despite these vast distances and fundamental barriers, despite the isolation imposed by the light year, we have learned an immense amount about the universe. We have mapped billions of stars, measuring their distances with increasing precision. We have discovered thousands of exoplanets orbiting other stars, some of which may be habitable. We have observed galaxies billions of light years away, seeing them as they were in the early universe, just after the Big Bang. The light year has been our fundamental tool for measuring and understanding these cosmic distances, for mapping the universe and our place within it. Let's conclude where we began. A light year is the distance light travels in 1 year, 9.46 trillion kilometers, a number so vast it defies our ability to comprehend. A distance so immense it makes our planet seem insignificantly tiny. But you don't have to fully understand it intuitively to appreciate what it represents. You can appreciate that the universe is vast beyond our complete grasp. You can appreciate that the light from distant stars has travelled for years, decades, centuries, or even millennia to reach your eyes tonight. You can appreciate that we live in a small corner of a vast universe on a tiny planet orbiting an ordinary star in one galaxy among trillions. There is something profoundly humbling about understanding the light year and the distances they represent. It reminds us how tiny we are in the grand scheme of things, how fleeting our individual lives are compared to cosmic timescales, how isolated we are in space, separated even from our nearest stellar neighbours by distances that would take thousands of years to cross with any technology we can currently build. It puts our concerns and anxieties and problems into proper perspective, showing us that from a cosmic vantage point, the things that seem so crucial in our daily lives are temporary and localized. But there is also something empowering about this knowledge. We figured this out. Despite being tiny creatures on a tiny planet, we have measured these immense distances. We have understood our place in the universe. We have built telescopes and spacecraft and developed mathematical frameworks that allow us to see and understand things billions of light years away. We are small, confined to a tiny world for now, but we are also incredibly capable. We are conscious beings who can understand the universe that created us. Those who can look up at the night sky and understand what we are seeing. Those who can contemplate the infinite and our own insignificance all at once. We can feel both humbled and empowered by the same knowledge. And perhaps that is the most important thing to take away from understanding the light year. Not just the technical definition, not just the mathematics of 9, 46 trillion kilometers, but what it means for us as a species, for our future, for our place in the universe. We stand at a unique moment in history. We are the first generation of humans to truly understand the scale of the universe. Our ancestors looked up at the same stars, wondered the same questions, but they did not have the tools or the knowledge to measure the answers. They could not have known that stars were distant suns. They could not have known that those suns were light years away. They could not have understood the vast distances that separate us from the rest of the cosmos. But we can. We have measured these distances. We have calculated them with precision. We know that Proxima Centauri is 4.24 light years away. We know that the Andromeda Galaxy is 2.5 million light years away. We know that the observable universe stretches 93 billion light years across space. These are not guesses or estimates. They are measurements backed by decades of careful observation and calculation. This knowledge changes us. It has to. When you truly grasp that the nearest star will take thousands of years to reach with our current technology, when you comprehend that light from distant galaxies has travelled for billions of years to reach your eyes, when you understand that we may be fundamentally isolated by the vast distances of space, it changes your perspective on everything. It makes our differences seem smaller. The things we argue about, the borders we draw, the conflicts we engage in, all of it is happening on one tiny planet in a vast universe. We are all on this small world separated from our nearest stellar neighbours by distances measured in light years. From that perspective, the things that divide us seem less important than the things we share. It also makes our existence seem more precious. If we are alone or effectively alone because we cannot reach anyone else across the light years that separate us, then what we do here is immeasurably important. We may be the only consciousness in our region of space. The only intelligence is capable of contemplating the universe and understanding what we are seeing. The only beings capable of creating art, discovering scientific truths, feeling love and compassion and wonder. That is a profound responsibility. It means we need to care for this planet, this tiny island of life in the cosmic ocean. It means we need to preserve and protect the knowledge we have gained, the understanding we have developed. It means we need to think long-term, not just about the next year or the next decade, but about the next century, the next millennium, the long future of humanity among the stars. The light year is not just a unit of measurement. It's a reminder of our place in the universe, a reminder that we are part of something far grander than ourselves, but also unique and precious within that vastness. A reminder that the stars are both incredibly distant and intimately connected to us through the light that bridges cosmic gulfs. Every time you look up at the night sky, you're participating in something ancient and profound. You're looking across light years. You're looking back in time. You're witnessing the universe in all its glory. And you are a part of that universe made of the same atoms, obeying the same laws of physics, connected by the same fundamental forces that govern everything from the smallest particle to the largest galaxy cluster. That is the true meaning of a light year. Not just distance, but connection. Not just isolation, but belonging. Not just our smallness, but our significance within that smallness. Thank you for joining me on this journey through space and time. If you found this exploration valuable, a like or subscribe would mean the world. It helps me continue to make these deep dives into the cosmos. And remember though, light years represent distances almost beyond comprehension. They're also what connects us to the stars. Every time you look up at the night sky, you're looking across light years. You're seeing the universe. And the universe, vast as it is yours to explore. Good night. And may you never look at the stars the same way again.